Most people use transformers every day without realizing it. Every time ChatGPT answers a question, every time an AI summarizes a document, translates a sentence, writes code, or generates an image from a prompt, there is a very good chance that a transformer is working somewhere underneath. But when you look at a transformer architecture diagram for the first time, it looks almost intentionally confusing. You see boxes called multi-head attention, positional encoding, feed, forward networks, residual connections, layer normalization, encoders, decoders, keys, and values. It feels like somebody took a simple idea and buried it under 20 layers of terminology. So in this video, I want to rebuild the transformer from the ground up. Not by memorizing the diagram, but by understanding the problem each component is trying to solve. Let's start with the most important idea. A transformer is essentially a machine that looks at a collection of tokens and continuously asks one question: which other tokens should each token pay attention to? Imagine I give the model this sentence: the animal didn't cross the street because it was too tired. What does the word "it" refer to? A human immediately understands that it probably refers to the animal, but a computer does not naturally understand relationships between words. It only sees symbols that have been converted into numbers. The transformer's job is to examine the words in context and discover which words are connected. In this case, the word "it" should pay strong attention to animal, and perhaps also to tired. That mechanism is called attention, and it is the heart of the entire architecture. Before attention can happen, however, the model first needs to turn language into numbers. A transformer does not directly read words. It reads tokens. A token might be a complete word, part of a word, punctuation, or even a space, depending on the tokenizer. For example, a word like unbelievable might be stored as one token, or it could be divided into pieces such as un, believe, and able. Each token is assigned an ID, but those IDs alone do not contain any useful meaning. Token 500 is not mathematically more meaningful than token 300. So the model passes each token through an embedding table. An embedding is simply a list of numbers, usually called a vector. You can think of this vector as the token's coordinates inside a very large mathematical space. Words used in similar situations tend to develop similar representations. The vectors for cat and dog might be closer to each other than the vectors for cat and economics. But there is a problem. If I give the transformer the sentences, the dog chased the cat and the cat chased the dog, they contain exactly the same tokens. The order is different, and that difference completely changes the meaning. Attention by itself does not automatically understand order. It sees a set of token vectors, but it needs additional information to know which token comes first, second, or third. That is why transformers use positional information. In the original transformer, this was done with positional encoding based on sine and cosine functions. Modern models may use learned positional embeddings or techniques, such as rotary positional embeddings, often called rope. The implementation can vary, but the purpose is the same. Inject information about token position into the representation. Now each token vector contains two kinds of information: what the token is and where it appears. At this point, the tokens are ready to enter the main transformer layers. This is where self-attention begins. For every token, the model creates three new vectors called the query, key, and value. These names sound more complicated than the idea really is. I like to think of the query as what a token is looking for. The key represents what a token can be matched with. The value represents the information that the token can provide. Imagine a search engine. You type a search query. The system compares that query with the indexed keys of different documents. When it finds a strong match, it retrieves the useful content, which is the value. Self-attention does something similar, except every token is searching through all the other tokens in the sequence. Let S return to the word "it." In our sentence, the query vector for it might be looking for a likely noun that can be tired. The key vector for animal might match that query strongly. The keys for street or because would probably match less strongly. The model calculates these matches using dot products. A larger dot product means the query and key point in more similar directions, suggesting a stronger relationship. The model then scales those scores and passes them through a softmax function. Softmax converts the raw scores into attention weights that add up to 1. If animal receives an attention weight of 0.7, tired receives 0.15, and the remaining words share the other 0.15, the representation of it will be influenced mostly by animal. The model multiplies those attention weights by the value vectors and combines the results. So after self-attention, the representation of it is no longer just a generic representation of the word it. It has become a contextual representation of it. In this particular sentence, that difference is extremely important. The word bank in riverbank should develop a different contextual representation from bank in bank account. The original token may be identical, but attention allows its meaning to change based on the surrounding words. This operation is usually summarized with a famous formula: attention equals softmax of Q times K transpose, divided by the square root of the key dimension multiplied by V. You do not need to memorize the formula. The basic process is more important. Compare queries with keys, turn the scores into weights, and use those weights to mix values. But transformers do not use only one attention calculation. They use multi-head attention. Why multiple heads? Because language contains many different types of relationships at the same time. One attention head might focus on grammar, another might connect pronouns with nouns, another might track the relationship between a verb and its object, another might identify long-distance dependencies between words that are far apart. Each head has its own learned query, key, and value transformations. This allows different heads to examine the same sentence from different perspectives. The results of these heads are then combined and projected back into a single representation. This does not mean we can always assign a clean human explanation to every head. Real models are messier than that. But multi-head attention gives the network multiple channels for discovering useful patterns. After attention, the information passes through a feed, forward neural network. This part is easy to underestimate because attention gets most of the publicity. But the feed-forward network is a major part of the model's computational power and usually contains a large percentage of its parameters. Attention allows tokens to exchange information. The feed-forward network processes that information independently for each token. A simple way to think about it is this: attention gathers the relevant context, and the feed-forward network transforms what has been gathered. The same feed-forward network is applied to every token position, but because each token now contains different contextual information, the output is different for each token. Inside this network, the representation is usually expanded into a much larger dimension, passed through an activation function, and then compressed back down. This gives the model space to create, combine, and filter features around both the attention block and the feed-forward block. We also have residual connections. Instead of completely replacing the old representation, the model adds the new output to the original input. In other words, a layer does not have to rebuild everything from scratch. It can preserve existing information and only learn what needs to be changed. Residual connections are one of the reasons very deep neural networks can be trained effectively. They improve the flow of information and gradients through many layers. Transformers also use layer normalization, which helps keep the values inside the network well behaved during training. Depending on the architecture, normalization may happen before or after the attention and feed-forward operations. Modern large language models often use a pre-normalization design, where the input is normalized before entering each major block. Now, take everything we have discussed: self-attention, multi-head attention, feed-forward networks, residual connections, and normalization, and stack it again and again. That stack is what gives a transformer depth. The first layers may learn relatively simple relationships. Higher layers can combine those relationships into more abstract patterns involving syntax, meaning facts, reasoning strategies, or writing style. No single layer fully understands the sentence. The representation is gradually refined as it moves through the network. The original transformer introduced in 2017 had two major sections: an encoder and a decoder. The encoder reads an input sequence and builds rich contextual representations. The decoder generates an output sequence one token at a time while paying attention to the encoder's output. This structure is especially useful for tasks such as translation. The encoder could read an English sentence, while the decoder generates the French translation. Models such as the original BERT primarily use the encoder side. They are especially good at understanding or classifying existing text. Models such as GPT primarily use the decoder side. They are designed to generate text, and encoder-decoder models such as T5 use both sides. When people talk about large language models today, they are often talking about decoder-only transformers, so let us focus on how that works. Suppose the prompt is: the capital of France is. The model processes the tokens and tries to predict the next token. It might assign a very high probability to Paris, smaller probabilities to other city names, and extremely low probabilities to unrelated words. Once it chooses or samples the next token, that token is added to the sequence. The entire process repeats to generate the following token. This is autoregressive generation. Predict one token, append it, and then predict the next. But there is an important rule. When predicting the next token, the model must not see future tokens. During training, the complete sentence may already be available, but allowing the model to look ahead would be cheating. So decoder-only transformers use causal masking. The attention matrix is masked so that each token can attend only to itself and earlier tokens. It cannot access tokens that appear later in the sequence. This forces the model to learn genuine next token prediction. Now you might wonder why next token prediction produces something that appears intelligent. After all, predicting the next word sounds like advanced autocomplete. But to predict text accurately across billions or trillions of examples, the model must learn an enormous amount about the patterns behind the text. It needs to learn grammar, facts, styles, relationships between concepts, common reasoning structures, programming syntax, and the ways humans answer different types of questions. The model is not simply storing a list of sentences. It is compressing statistical patterns from its training data into its parameters. During training, the model sees a sequence, predicts the next token, compares its prediction with the correct token, and calculates an error called the loss. Backpropagation then adjusts the model's parameters slightly to reduce that error. This process happens over and over again across massive datasets. Queries, keys, values, embeddings, feed, forward weights, and output projections all begin mostly random. Training gradually shapes them into a system that can model language. Once the final transformer layer produces its output, the representation at the current position is converted into a score for every possible token in the vocabulary. These scores are called logits. A softmax function can turn the logits into probabilities. The model can then choose the most likely token or sample from several likely options. The sampling method has a major effect on the output. Using the highest probability token every time can make the response predictable and repetitive. Increasing temperature makes the distribution flatter and the output more varied. Top K and top P sampling restrict the choices to a smaller group of plausible tokens. So the final answer is not stored somewhere inside the model, waiting to be retrieved. It is generated token by token from probability distributions. One of the biggest advantages of the transformer over older recurrent neural networks is parallel processing. An RNN reads a sequence step by step. It processes one token, updates its hidden state, and then moves to the next token. That sequential structure makes training slow and can make long-range relationships difficult to preserve. A transformer can process all tokens in a training sequence simultaneously. Attention directly connects distant positions, so the first token can interact with the 100th token without information traveling through 98 intermediate steps. This parallelism made it possible to scale language models much more aggressively. However, attention also has a major weakness. In standard self-attention, every token compares itself with every other token. If the sequence length doubles, the number of comparisons grows by roughly 4 times. That quadratic cost makes extremely long contexts expensive. This is why researchers continue to develop more efficient attention methods, sparse attention patterns, sliding windows, memory systems, and other alternatives. Another limitation is that transformers do not automatically know whether something is true. They learn patterns from data and generate likely continuations. A fluent answer can still be wrong. The architecture is extremely powerful, but it is not a built-in truth engine. That is why modern AI systems often combine transformers with tools such as search engines, retrieval systems, code execution, calculators, databases, and external verification. So when you strip away the intimidating terminology, the transformer is built from a surprisingly understandable loop. Turn tokens into vectors. Add information about position. Let each token decide which other tokens matter. Mix the relevant information. Transform it through a neural network. Repeat this process through many layers. Then use the final representation to predict what comes next. Embeddings tell the model what entered the system. Positional information tells it where everything is. Attention tells it what is related. Feed, forward networks process those relationships. Residual connections preserve information. Normalization stabilizes the computation. Stacked layers create depth, and the output layer turns everything into the next token probabilities. That is the transformer architecture. It is not magic, and no single component explains everything modern AI can do. The power comes from combining these relatively simple operations, training them at enormous scale, and repeating them billions of times across huge amounts of data. Once you understand attention as information routing, the entire diagram becomes much less mysterious, and the next time an AI writes an answer, summarizes a document, or completes a piece of code, you can imagine what is happening underneath. Thousands of token representations repeatedly looking at one another, deciding what matters, exchanging information, and gradually constructing the next token.